Good morning, everyone. I hope you are doing all right. And I'm hoping you can hear me just fine. So far we learned two main basic physics. Okay. So two main principle of basic physics. One is kinematics. Another one is dynamics or laws of motion, also known as Newton's laws of motion. And then we also learn how to use them, how to use kinematic equation to solve problem, and how to use Newton's laws of motion to solve problem. So the application of dynamics, will continue that today by learning how to use it when object is moving in circular path or part of the circle. Okay, we'll continue that. But before we do that, we're going to talk about a force uh, that arises in a spring. So, for example, when we pull a spring, I'm losing my spring. So, when we pull a spring, spring pulls us back, right? So, we call that spring force. And why is that important? Because all the materials are made up of atoms or molecules. And because of that, what happens is that the bonding between those atoms and molecules, they act like a spring. So by learning about that force, we can also learn about, for example, let's say, how much force, compression force, a iron rod or our bone can withstand, or when it's going to break, how much force we can apply, and so on. What's the limit? So those kind of thing we can learn when we learn about this spring force. So in our list of these different forces, last class we talked about drag force, and we briefly and quickly kind of talked about this spring force as well. So here I'm starting from right there, the spring force, and they're everywhere in the nature. All matters are made up of atoms and molecules, and this is like a cartoon or a model of, let's say, a small part of matter, chunk of matter. And this spring-like drawing you see here, they are basically bond. So they behave like a spring. So that's what we know. So because of that, we want to know, how the spring behaves. So here is a spring, and we are applying force on the spring. So there is applied force. So you hang a mass on a spring, it gets pulled down, so it stretches. At the same time, what happens? The spring pulls the mass back. So that force is the spring force we're talking about. And here I'm writing that as a force with the subscript S, means spring, okay? And the weight is the applied force here. And once we put weight on the spring, what happens? Spring comes to the equilibrium situation. So for example, here I have a little tiny weight here. So if I put that one there, what happens? The weight, depending on how heavy the weight is, the spring gonna come a little bit down or more down. And I'm sure you have seen and encountered this kind of situation. So when we do careful example, what we find is that more the spring gets stretched, the spring applies the restoring force, what we call the spring force. at the same proportion. So they are equal, okay? So what are equal? So for example, there is a spring and let's say it was here before we put the weight, now it is here. So that means this is what we call displacement or simply X here, okay? So this is the stretch. So the experiment shows that larger the stretch, larger the spring force. They are proportional. And how much a spring stretches depends on how large the force we are applying. But at the same time, there are these different kind of springs. Some spring we can easily stretch, others they are very difficult to stretch or compress. So to describe that nature of, like how hard or how easy it is to stretch or compress a spring, we introduce what we call spring constant. So basically, the origin is purely mathematical. Basically, what happens is when we do experiment, longer the x, larger the force we get. But how much is exactly force we cannot calculate just from the position or the stretch, because the stretch is length and force is force, right? So they don't have same unit, so they cannot be equal. So what we do is we use what we call proportionality constant to convert this equation into equal, equation with the equal sign. And that's where this spring constant comes in, okay? So that's where the spring constant K comes in. So if you can easily stretch a spring with very small force or small force, that means it has relatively smaller K. But if you have a spring, for example, that goes in the, let's say that is connected to the body of the car and the wheel, shock absorber kind of thingy, that acts like shock absorber. Have you ever looked underneath the, car near the, the tires? You see there is this coil spring. Sometimes it's inside the rubber, so may not be obviously visible. So that shock absorber, for example, if you try to push that with our strength, we cannot push it. It's like a steel rod, although it is spring safe. But with the weight of the car, it gets a little bit pushed, so that way it keeps the motion smooth. Okay, smoother, I should say. So that's the spring constant, folks. And you see there is a negative sign. So this x, the stretch, is a vector quantity. So for example, if we are pulling this spring down, then what happens? The force is acting up. So force and stretch, they are in opposite direction. So when we write the equation that, with the two vectors that are pointing in opposite direction, to represent that direction, we put the negative sign here. So negative sign simply means direction here, nothing more. What does it mean again? The direction of spring force is opposite to the change in length of the spring. So if we stretch, means if we pull it down, for example, in the spring that's hanging something like this, then the spring force is up. But if we push the spring, then the spring force is going to be down. So if we try to compress a spring, then the spring force acts in the opposite direction, but the proportionality sign still holds. So in the lab, we can do simple experiments, something like this. So there is a spring without any extra mass over here. You put a mass, then there is a stretch, and then now you double the mass. See, you see there, similar mass, double. And then if you look at the stretch over here, this stretch here is, if we were to compare this stretch here with this stretch over there, what do we find? If we do careful measurement, this new stretch is double compared to this stretch. Why? Because the mass is double. Mass double means weight is also double because weight is simply mass times g. So when you double the mass, the whole weight also becomes double. Okay. So here we are talking in terms of applied force because that's the easy to measure. And applied force is also opposite to the spring force in terms of direction, but the value is same. So for the value, we can basically, we may switch between applied force and the spring force because they have same value. So by measuring applied value, which is easier to measure, it's easier to tell how much spring force is. Okay. How do we know that? From this experiment, or this Hooke's law is established by this kind of experiment. Okay. So that's that. So value of the applied force and the spring force, they are same, but they are in opposite direction. So what that means, applied force and the stretch or compression, they are in same direction. So notice the difference between applied force versus spring force. They have same value, but they are in opposite direction. Applied force is the force with which you pull the spring, and spring force is the force with which the spring itself pulls your hand, right? When you are pulling spring down, the spring itself is also pulling the hand up. So keep that in mind. So there is difference. So they have, what's the difference? Value is same, the direction is opposite. And because of that, what happens is sometimes you may see Hooke's law written simply F as a kx. So that means in that case, if there is no negative sign, basically, we are simply talking about applied force, which is equal in value to the spring force. Okay. So when we do this kind of experiment, what we can do is we can carefully measure this stretch and how much force we are applying and make plot of that. If we do that, what we get straight line trend, okay? And slope of that straight line gives you the spring constant. So you can actually calculate the spring constant of a string by designing very simple experiment like this. Okay. So that's the Hooke's law, folks. So what happens is if we keep pulling a spring, then it never snap back as much as we pulled. So there is a limit up to which it acts or follows the Hooke's law. After that, what happens? Even a bit smaller force can stretch it more and more, okay? So when that happens, we say, okay, it's not following the Hooke's law. So as long as it's following the Hooke's law, we say, okay, it is elastic. Once it does not, or once it stops following the Hooke's law, we call it plastic. And how do you know that? So if you were to make similar force and the stretch graph, what happens is where it is behaving nicely with a straight line with just one slope, constant slope, then during that region, that linear region, it is following the Hooke's law. Okay, it's following Hooke's law. So that means it is elastic. And after that, what happens? You see, it gets stretched more with the smaller application of force. Then when that happens, we say, okay, that's a Peller region, or in popular world, we call that, in popular word, we call that plastic. So for example, if you have, let's say, a grocery bag, these days it's, in Colorado, it's discouraged to use grocery bag as a plastic bag. But anyway, let's say if you have some sort of plastic bag and if you stretch, what happens? If you stretch, it just remains there. It does not snap back like a spring, okay? So that's why the name plastic, okay? So even our bone has that kind of limit. For example, if you jump on the floor from, let's say, your bed, you may not break your bone. What happens in that case? Your bone gets a bit compressed, and then later what happens? It comes back to its original position. So your bone is still elastic. But for example, if you, let's say, jump from, you know, top of the building, then what happens? Your bone breaks. So what happens? The amount of force that's applied becomes or exceeds this elastic limit, and then it becomes plastic. And eventually, if it's like breakable material, then it breaks. Okay, that's we call breaking point. So we'll look at the actual graph of the bone of a bone. Okay. But before we do that, here is a question for you. So F here represents the spring force as indicated here. Okay, let's do 30 more seconds. And 5 more seconds. 5, 4, 3, 2, 1, and it stops. Okay, let's see what we got. Mostly equal to F, and that is correct answer because it is in equilibrium. Equilibrium means net force must be 0. If I were to make free body diagram, F, mg, so acceleration 0 means this force is balancing the mg, and that's what we talked in the previous slide. Okay. So that's the spring, but let's say we want to look at the rods, for example, bone. So what happens in that case? Yes, their internal structure is like that once we go to the atomic level, but when we look at it, what happens? A rod does not look like a spring. And it turns out that if we apply same amount of force in a very thin wire versus on a rod, the amount it stretches are different. So because of that, what happens is it turns out in case of rod, bone, the diameter of the bone or the rod also matters, okay? So we need to include that in a Hooke's law. So when we include that, it becomes what we call generalized Hooke's law. So diameter is this, but we talk in terms of this cross-sectional area here. So if you know diameter or radius, the area gonna be, in terms of radius, it's pi r squared. In terms of diameter, it is pi d squared over 4, okay? And so this is the area we're talking about. So for example, and so rather than just how much force we are applying, what do is we divide that force with the area at which the force is acting, or in another way around, how big the rod is. Is it tiny, like a wire? or it's a bit bigger or even bigger, right? So that is included by using area. So when we divide force by area, now we call that stress. So we talk in terms of how much stress we are applying on the rod or on the bone rather than just force, okay? So force has a unit Newton, so area has a unit meter squared. So because of that, the stress has a unit Newton over square meter. So there are different kind of stress, okay? So here we are talking about a particular kind which acts directly, along the length or opposite to the length. Sometimes what happens is we can squeeze a ball. So in that case, it's going to be volume. Whole volume is acting on whole volume. Okay. So that's another kind of stress. Sometimes we may be pushing something and object gets tilted. Okay. So that's it. Different kind of stress. But in this case, we're going to be focusing only one stress. If you are interested in another kind of stresses, please take a look at the book. But here I'll be talking about just one kind of stress, which is tensile. And which is that? What is that? The stress that usually applies to a rod kind of structure. Okay. So this is stress, and we call that tensile stress. And then strain is now, see, this would be, for example, in case of a spring, it would be just delta x. Now we are writing in terms of length of the rod to differentiate it from the spring, okay? And we divide that by the whole length. So it is kind of relative stretch on the, the length of the rod, and it's called strain. And since this is a ratio of 2 units, so for example, change in length gonna also have unit meter, and original length also gonna have unit meter. So the unit cancels, giving us unitless quantity. So now, remember, for the Hooke's law, what did we do? We talked in terms of spring force and the stretch. That's how we talked. Now for the rod or bone kind of, rod kind of structure, we talk in terms of stress and strain. So just like force is proportional to the stretch in case of Hooke's law, similarly, the stress is proportional to the strain, and that relationship is called generalized Hooke's law. Just like we introduced a spring constant to get rid of this proportional sign to equal sign, we do the same thing. But in this case, the constant is going to be different, not the same K we have for the spring. And that is denoted by uppercase Y, okay? And that's called Young's modulus or elastic modulus. So this is one relation that applies to the case when we are trying to stretch a rod kind of object, rod-shaped object, or trying to compress. So for example, when make this tall building with the, let's say steel rods in them, with the pillar with this steel rod, what happens? In that kind of architecture, it has to bear load, okay? So now if you have to build just a 1-story or 2-story building versus like 10-story, 20-story building, how thick, what should be the area of the rod you are using, gonna be totally different. So this equation gonna help you to actually determine or estimate, how big the rod has to be to withstand that load. Similarly, in case of breezes as well, what happens is a breeze has this steel structure. So On a hot summer day, it tends to expand or becomes a bit bigger. And in that case, it's like now it has a strain. Why? Because it's trying to expand. When we hit something, it tries to become longer. We'll talk about that expansion of object in at another chapter. But the another application we see is on the breezes as well. So that develops a stress on the side of the road. If we don't manage that properly, then what's going to happen? There are going to be, let's say, either breeze going to break or there are going to be some push or crack on the side of the breeze and so on. So building, breeze, and so on. So if you are architecture or civil engineer, something like that becomes important in your daily life. But many of you I know are life science major. So in that case, maybe they're going to be, for example, bone, right? Or artificial material you can manufacture. And when you do that, what happens is that kind of material can be used as, for example, kneecaps or knee replacement of knee, and so on. So in that case, what happens? Yeah, the knee is made up of certain organic material, of course. So we can do experiment and figure out what's the value of Y for that kind of material. You know what's in our knee material that our knee is made up of. And then when we try to artificial knee, we try to manufacture artificial knee, we want to replace that by the material, artificial material that has about the similar value of, similar material that has the same Young's modulus value or elastic modulus. So that's what we want, okay? So we do not want to just put the steel as a knee replacement, okay? So that way the value of Y, understanding what that is, elastic modulus becomes interesting, okay? So there is a manufactured or artificial knee over there, okay? And here is a study, how bone of different age people and different kind of condition, people with a different kind of condition on the bone. This study was done. If you are interested in detail about, okay, how bone behaves under the stress, different kind of stress, and then you can go to this link and then look at the paper over there. But I simply brought the result here. So what we find is if there is a healthy person and young person, you see this line is straight up to very long, like for up to large stress. So it can withstand large stress. So that's why as long as we are, like let's say young, we can jump off from certain height and our bone not gonna break. But once we grow older and once we have, let's say, condition, then what happens is the elastic property is in a very small window of the stress. So that's why once you have this kind of condition, for example, osteoporosis, what happens? Your bone may break even when you just fall, not just jumping from the bed on the floor, not just jumping off from some tall table, but simple stress may also cause this breaking point. So that's what this study is showing. Okay. So while doing that, they also looked at, how the color of that bone structure changes at different strain. So for example, zero strain means there is no strain, right? In normal condition, let's say you are just sleeping or sitting on a chair and your bone does not, you know, uh, being pulled or pushed by anything, even with your weight. And then now you increase that to 14%, for example, what happens? You observe more whitening over there, means it gets warmer. And the way this image is generated, what happens? Warmer the material is, it produces whiter image. Okay, and so on. So that's how they studied, how it behaves and so on. Kind of interesting article. So if you are interested, you can go to this uh, link. It is in my posted slides on the class slide folder, right? All of these slides are there, and you can copy this and paste on your browser if you are interested. Okay, so that's about this elastic force or spring force or spring-like force, okay? And this equation works for the bonding between elements as well. Same equation can be applied even if you are just looking at the bond, force on the bond when you move the atoms, okay? So that's why this is kind of important. Now I'm going to move to application of Newton's law again, back. But in this case, object is moving in circle or part of circle. So when we talked about finding direction of acceleration, drawing change in velocity vector, we talked about this kind of situation, how to draw that and how to figure out direction of acceleration. And here I'm showing you full circle, but it doesn't have to be full circle. So in our daily life, so for example, when we are turning on the corner, the car we are driving, we are going in a part of circle. Okay, it may not be full circle, but it's part of circle. Similarly, when we are exiting highway or entering highway, we may go through that circular or part of circular ramp. So those kind of situation. In this kind of situation, we can use this, go back to the method we learned, for example, how to draw difference, change in velocity vector, okay, using those 2 or 3 steps method. So you bring them and draw tails together, and then from tip of initial to tip of final, right? And then what we see is this delta V is pointing towards the, so for example, we are looking at this point and that point. On average, between these 2 points would be this point. So if I draw this from here, it's pointing toward the center of the circle. So here, if you pay attention, what you find is it says uniform circular motion. So in circular motion, velocity is changing. So because of that, it's accelerating. But how velocity can change? So value of velocity can change, or simply direction of velocity can change, or both of them can change. That produces change in velocity. Velocity means value and direction, right? So in that case, what happens is when we look at here, even if the velocity is, the value of the velocity is not changing, it can be accelerating when it's moving in circle because direction of the velocity is changing, okay? So direction of velocity causing the acceleration. So if the value of velocity, let's say that is speed, when you are moving in a part of circle or circle where speed of the object is not changing. So for example, let's suppose you are going in a ramp and the speed limit of ramp is 40 miles per hour. And throughout the ramp, if you are driving 40 miles per hour, your speed is same. But since you are constantly changing direction, your velocity is not same. Your velocity is changing because of simply change in direction. So when we look at this, take account of that change in direction, See, the length of both arrows, they are same. So that means value is not changing. So even when value is not changing, it can be accelerating. And that kind of acceleration is called uniform motion. Okay, uniform circular motion, where speed is not changing, only the direction is changing. So that shows us when it is uniform means when speed is not changing, what happens? Acceleration points directly towards the center of that circular path. So, for example, if I am just driving in a ramp that is just like this, then how do I figure out direction of acceleration? As long as I am driving with constant speed. So imagine this is part of big circle. Oh, my circle looks like potato now. So center is here. So that means the radius would be something like that. So if the car is there, it's going to be pointing in that direction. What is it? Acceleration. When car is here, see center is there. So that means it would be pointing in that direction. When speed is not changing. What if the speed is also changing while you are driving? Okay. So now you are trying to get into highway. You decided to go higher and higher speed in this part of this circle. Okay. Then what's the direction of acceleration? How do you find that? So if you know the velocities, for example, here, velocity is going something like that. And over here, you are increasing speed means the length gonna be now longer, okay? So in that case, your initial is this and BF is this. Now you can use the same method to figure that out. So for example, let's say a pendulum is swinging. Let's suppose a pendulum is swinging. When it's going back and forth, see, it is moving in part of circle. So it's moving in part of circle. Okay. So it has acceleration. And the velocity is not same everywhere in that part of the circle. So velocity could be changing. What's the direction when that thing is at a certain point? Or let's say, what's the average acceleration going from this point to that point? To find that, you can use the same method. No matter whether the speed is changing or not, beauty of this method is you can use the same method, same steps. And so that's the direction. How about the value of the acceleration? So this can be derived, but here I'm not going to derive it. What's going to do rather is that I'm just writing the equation. So this is the speed. So acceleration at any point. So for example, here, direction of acceleration is this. So what's the value of acceleration? V square over R. V, what is V? V is the speed at that point. Okay, V is the speed at that point. Square that and divide that by the radius of the circular path. So for example, in this case, this would be the radius, this whole length gonna be the radius. So if you know what's speed here and you know radius of the circular path, you know the value of acceleration. How do you know the direction? Using this method. So now when object is moving in circular path, you learn how to find value and direction of the acceleration. So now you are ready to use Newton's second law. In Newton's second law, what happens? Sum of forces in a particular direction is mass times acceleration in that direction, right? So in this case, sum of force, what we want? Sum of force in the direction of radius is equal to mass times acceleration in that direction. So that's why this acceleration is also called radial acceleration. And you may see there is subscript R sometimes, or there may be subscript C, also known as centripetal. because it's pointing towards the center. Okay. Remember, it points exactly towards the center when speed is not changing, but the overall acceleration of the object could be pointing slightly off from the center when speed is also changing, when object is moving in part of circle. And here is this question for you. Remember those two steps, and there is one velocity here, and this length of this velocity you can see is longer than this one here, v2. Or you can say this is vf, this is vi. So vf is shorter than vi, so that means speed is changing. Not just the velocity, but also the speed is changing. Value of velocity is changing. Okay, so now what's the direction of acceleration? So that's the question I'm asking you. And the possible answers are shown here, and that's written there. So you want to draw using those two methods, and then choose the answer. Thirty more seconds. And 5 more seconds. 5, 4, 3, 2, 1, and it stops. Okay. Let's see what we got here. Oh, we got all of them. A and C, that is kind of competing here. But we also got B, which is towards the center. So B would be correct answer if BI and BF, they had same length, okay? If they had same length, then B would be correct answer. But since it is changing, it's going to be off from the direct center. So which one is it? So I don't know, but what I do is I know how to do or figure out. So for example, my BF is right there, and BI, let's move the tail of BI to the tail of BF. So what I need to be careful while drawing is this BI is longer than BF. So I need to draw that. Okay, you don't have to write it, but remember, this is longer than this one here while drawing that. So now this is the first step on drawing change in velocity vector. And the second step would be going from tip of initial to tip of final. So when we do that, what happens is it is kind of pointing closely towards that direction. So it's tilted on the left from this B here. So that's why it looks like A is correct answer in this case. And if you are wondering, what if I draw B2 over there? So B2 is kind of almost horizontal, but shorter. So if I draw that, still gonna be same. BF, BI, So tip of VI to VF, so it's pointing in that direction. Okay. So that's why A is the correct answer in this case. So what did we learn? The total acceleration is towards the center of the circle if the speed is constant, but if the speed is changing, it may be off from the the center. And here in this case, what's happening is slowing down. So it is kind of a bit backward. See, you can see that. It's slowing down means kind of backward, not directly back because it is not moving in straight path, but kind of backward. If it was speeding up, probably this would be the answer. If the B2 was longer than BI, then this would be the correct answer in that case. When it's accelerating, when speed is increasing, the acceleration is more towards the original velocity. When it's slowing down, it's opposite to the velocity we learned when something is moving in straight line. It is moving in part of circle, so that's why the acceleration is not directly backward, but slightly off. So when we have this kind of situation, what we can do is we can write acceleration in two components. So let's suppose this is our acceleration. So we can write its component, one like this, another like this B that's towards the center. So this is radial, and this is tangential. Okay, like a tangent. If I were to draw that line here, that looks like a tangent on that curve over there. Okay, so that's why it's tangential. So when velocity is, value of the velocity is changing, there are possible two kinds of acceleration. So tangential acceleration, for that, to finding that, we need to compute how the velocity is changing. But for the radial acceleration, if we know speed at a particular point, this equation is still going to be true. The one that's pointing towards the center, this radial part, still going to be true. Okay. Here I'm writing in terms of speed and the radius of the circular path. And this can also be written in terms of radius and what we call angular speed. See, it's moving in circle, so we can describe motion in circle by writing in terms of angle as well. So that is called angular speed. Oh, what is it? How do we define? So just like linear speed is defined as a displacement over time interval, similarly, angular speed is defined as angular displacement. So that means displacement not in terms of just linear positions, rather in terms of angular positions. And that's what I'm writing here. Okay, so this change in angle, theta, remember, means angle. So change in angular position. So that's what that is. Okay, theta is angle, but when we combine that with the delta, that is change, right? And we also call that angular displacement. So just like linear displacement, for example, we write that as a final position minus initial position. Similarly, we write angular displacement as a difference between final angular position and initial angular position. So how do we look at it? For example, let's say something is moving in part of circle like this. So let's say this is your initial position. So you can say, okay, or maybe even usually we say that is 0. So let's say it's going something like that. Initially you spotted here. So this is going to be your, let's say, initial angular position. And then when it arrives here, the angle changed. So this whole thing going to be the final angular position. So for example, let's say if this was 10 degree and this whole thing is, let's say 35 degree. So theta I is 10 and theta F is 35, means the angular displacement in this case is final angular position minus initial angular position, means 35 minus 10 is 25 degree. And angular displacement, yes, angle displacement. So angles, we write them in degree, but in SI system, in scientific system, just like we don't use pound for the mass or the weight, rather we use kilogram, gram. Similarly, for the length, we use meter. Similarly, in SI system, the unit of angle is taken as a radian, okay? So unit of angle is radian. That's what we use. So, okay, what is radian? So we can define radian, but what happens is when something goes in one full circle, we say it goes through 360 degrees, right? Full circle is 360 degrees. So now in radians, it turns out to be 2 pi radians. So that's what we use to convert from degrees to radians. Okay. So what's the conversion factor? 360 degree is 2 pi radians. And in short, we may simply write RAD, rad for the radian. So that means 1 degree is 2 pi over 360 radian. Okay. So now, if I want to convert this 35 degree, what I have to do, I have to multiply this by 2 pi radian because I want radian and I want to get rid of degree. So I need to divide this by 360. So now this answer is in radian and this is slightly less than 2 pi, looks like. Oh, 35 versus 360, not just slightly less, a lot less than 2 pi, right? So you have to divide 35 by 360 and you'll get a fractional number times pi radian. If you want to convert that pi into numbers as well, then pi is 3.14 approximately. Okay, so we can write something like that. Okay, so that's about the unit of the angle, the SI unit we use. Now we want to go back to our original goal to define angular velocity. So this is angular displacement. So that means the unit of the angular displacement is going to be also radian, because difference between two angle going to have unit of angle, means the unit going to be still radian for this one. Now, just like average velocity, we can write average angular velocity by dividing by time interval. So AV here means simply average. And notice the notation. This is not W. It's curly, right? It's curly W. That is lower case omega. Uppercase omega is this. This is lowercase omega. Okay. So this is the uppercase. This is lowercase omega, and that's the notation we are using. So this is just like average velocity, but in terms of angle. So that's why angular change. So that's why we are writing something like that. Okay. So its unit gonna be radian. See, the unit of this is radian. Divide by that time, which is second. So it's gonna be radians per second. So that's the unit of angular speed or average angular speed. Okay. So when time interval is very small, then average becomes instantaneous at that moment, right? So basically unit is still same. So how this average angular speed is related to our average velocity, or simply angular speed is related to that? How is their relationship? They are both speed. So to do that, what we can do is we can look at, let's say, imagine rolling a tire. Okay. So for example, you start tire from here. So tire originally was there. And then what happened? You rolled it. So because of that, it arrived here, right? So now the one that was over there has arrived here. So with what angle it went through in that rotation, right? So that is the angular displacement. So that angular displacement, and if we go through the circumference of that tire, we call that linear distance, and that's how far you are moving, right? So how far you go in a car? When your tire spins once, whatever the circumference of your car tire is, that's how far forward you have gone in one spin. 2 spins, double that. 3 spins, triple that, and so on, right? So what happens is this angular displacement and this linear distance it travels, they are directly related through the radian. So delta theta is actually this over r, okay? And the definition of radian also comes from there when s and r are equal. Or what happens? The ratio is 1, means it's a 1 radian, okay? So anyway, so that gives you the relationship between this two displacement. It's like a linear displacement. This is like an angular displacement. So relationship is through the radius. Or another way, if you want to solve this equation, something like that, then this is what you get. Now, why am I doing this? Because I want to write the relationship between V and omega, linear speed and angular speed. And for that, I'm going to now define the average speed, linear speed, which is distance divided by time interval. So this linear distance here. So why notation is yes? Usually the notation is yes for the motion where, this displacement is taking place in part of a circle, also called arc. Okay. So what I'm doing here is I'm replacing this. So I want to go from linear to angular. So because of that, I'm using this equation or this equation here. So once I do that, what I find is I have this, which is same as this, means this is the angular speed, average angular speed. So that's the relationship between these two speeds. V is R times omega. So this is one equation you see in a formula sheet as well. Yeah, formula sheet also has this one. I think it is under the rotational kinematics or something like that. On the formula or equation sheet I have provided. So now see, I wrote, okay, radial acceleration is V square over R. So now if I use this relationship here, what do I find? V is R times omega, but there is squared, so I need to square it, and this is R. So that gives me R square omega square over R, and that gives me R omega square. So the the radial acceleration can be written either in terms of V square over R or R times omega square. So either in terms of linear speed or in terms of angular speed. So when do you use which one? It depends on what you are given or what you are asked to find, right? So whatever you are asked to find or whatever you are given, you can use equation for radial acceleration as either this V square over R or R times omega square or omega square times R. Okay, so that is that, and looks like it's 11:03 already. So let's take a break. Welcome back, folks. So in a week, we have a midterm, first midterm, and it will have a question similar to, what you see on the clicker question. For example, mostly all of them going to be multiple choices, but to solve some problem, you have to do the math. To answer some of the question, you have to do the math. And here is my guide for you to, prepare for the midterm worksheets. Thoroughly understand them, including explanation. A lot of multiple choice question gonna be from the explanation part. Okay. And then of course, clicker question and problem done in class. So they are all kind of related. Okay. So when you're looking at clicker question, so see if you can explain why a particular question is correct. Particular choice is the correct choice. And even better, why the remaining choices are not correct. Okay. Can you explain, argue that? Okay. So that's how critically you want to look at when going through the clicker question. So if you are using clicker app, all the questions with the answer is in your app. So memorizing just the answer not going to be that much helpful because the same question not going to be there most likely. Similar question, however, going to be there. So you need to understand. So it's better if you come back to the slides that I have posted. So they are empty. Go through the question, see if you, and then answer and write down why that is correct answer. And then go to the clicker app and check how many you did it right. Okay, so that's one way to do it. But all of you are grown-ups, you know what's best worked for you. So I let you decide on that. So for now, I like to move on. And I brought this question here. So in this case, this object is kind of here and it's moving in this circle. Okay. So when we do something like that, what happens is usually when it is going, it's moving with kind of constant speed along that horizontal circle. So now the question is, what is the direction of the radial acceleration, or what is the direction of the acceleration? And choices are there. So I'll let you answer, and you have a minute to answer this question. Thirty more seconds. 5 more seconds. 5, 4, 3, 2, 1, and it stops. Okay. So let's see what we got here. Mostly C, there are some B and D as well. Okay. So in this case, it's kind of moving with constant speed. So when something is moving in a circle or part of a circle with constant speed, then the acceleration going to be toward the center of the circle. So center being over here, I think yes, C is the best choice here. So when something is moving with constant speed in a circle or part of a circle, that's how the motion looks like. The radial acceleration is, as name suggests, towards the center, and velocity is tangential. So if you are spinning something over your head, oh, this thing is coming off. Almost I hit something here. I used to have a pendulum. I don't know where did it go, made up of wood. So when something is going in a circle, something like that, for example, overhead, right? If we let it go, what happens is it does not go in circle, it just goes straight. It shoots straight once we don't apply this force. Why? Because it's the tension force that causing it to go in circle, right? So if tension force is not there, in this case, what happens? Once I let it go, tension force is not there, means it will just keep moving in a straight line, as suggested by Newton's laws. So that's why the velocity is tangential to that circular path, not like this. The velocity does not line up with the circle. Remember, it is tangential. And the radial acceleration is towards the center, as name suggests, okay? But if the speed is changing, we can have radial acceleration and tangential acceleration. Tangential acceleration tells us, how the speed is changing, and radial acceleration tells us why this thing is going in circle. And we write Newton's second law like this, just like I said before, okay? So v square over r, or this can also be m r omega square, depending on what we know or what we are asked to find. So v, or it could be angular speed or linear speed. So for object moving in circular path, rather than writing RAD radial, most likely I'll be using this MAR. So this is like the same as So when we read this, what's going to happen? Sum of forces in a particular direction is equal to mass times acceleration in that direction. Same idea here, that direction is radial when something is moving in circle. Something is moving in circle because there is net force acting towards the center of the circle. How do I know? Because acceleration is towards the center of the circle. So that's how I like to use Newton's second law for object moving in circular path. Okay. So just the notational difference, otherwise theme is same. So what you have to do is you need to make free body diagram and choose one axis towards the center of, towards the radius of the circular path, because there is always a radial acceleration in that direction. So that way we can use Newton's second law. So we're going to be looking at some example here. But before that, I have a short video where there is a platform that can be rotated, okay? And there is a coin sitting on the table, okay? And you see there is a string, but the string is not attached to the coin, okay? Coin is not attached to that spring. So when we let it spin, how the coin gonna move? Let's see, okay? So coin first gonna move in circle. So why is it moving in circle? So for example, this one, when I rotate this over my head, is going. So I'm not doing this because I do not want to let it go and hit my screen and so on, okay? But you got the idea. There is this tension force that's making it go in circle. If the tension force wasn't there, it would just fly off. Similarly, there is this coin sitting on there and it goes in circle. So there must be, since it is moving in circle, there must be some net force acting towards the center of the circle. And the question is, what force keeps the coin on the circular path? Okay. And then once it leaves at, when the speed is large enough, it's not going to just stay there. We'll see what's going to happen, and it's going to take off from the table. When it leaves the table, which direction it's going to move, right? So those are the things you want to keep in mind while looking at it. So see, you saw it was there and it went in circle, so it is approximately moving in the circle, right? Yeah, I know it's kind of hard to see here, and this video is not high definition video. Oh, I want to go a little before that. Uh-oh. The thing is, when in PowerPoint mode, it's hard to control the speed. Okay, looks like with the mouse I can do that. So you see here, it is sliding away from the center. Did you notice that? Sliding away from the center. Let's go a little bit further. 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 See how it's sliding away from the center. How do I know it? See, we have a string. So it was sitting near the string, and then when it was, rotating with a certain speed, it went to in a circle. And once the speed increased, it started first sliding off from that, sliding away from the center. And then when it is at the, end of the table, what happens now? It leaves the table eventually. So this was very close to the string, and you can see now it is here. So it looks like it's going something like that. So that's the direction of velocity, okay? When it leaves the circular path. So once it leaves the table, nothing is pulling it towards the center. And the force that keeps the coin to the circular path is, what is that? I see there is a response, but with a question mark, right? What force is keeping it there, right? So it's not tied to the string, so that means it is not tension, of course. And gravitational force is acting down, so that means it's not acting towards the center of the circle. And we notice when it slides away from the center of the circle. So now in that case, it must be friction that's acting towards the center of the circle, okay? And any force that acts towards the center of the circle, we call that centripetal force. Like acceleration, we call that centripetal acceleration, right? Often I like to call it radial rather than centripetal. So centripetal force is, blanket statement for any kind of force that's acting towards the center. So in this case, if we be more specific, it is friction force. And in case of this mass attached to this, what force is the centripetal force in this case? It is, what force is the centripetal force in this case? So what force is acting towards the center in this case? What force acts through the string, folks? You know that. It's a tension, right? So centripetal force is a blanket statement. So we have to be more specific about it, like a tension. Is it tension? Is it friction force or something else? Okay. So now here is a question related to the video we saw. So let's suppose that coin placed is rotating around this much RPM. Ooh, what is that? It is for now, it is angular speed. It does not have correct unit for us, but that is angular, speed. RPM, full form of RPM, probably you guys know that. Revolution per minute or rotation per minute, okay? So RPM and friction coefficient is given. So since it is sliding, like it's trying to slide, it is static friction force. Before it starts sliding, it was trying to slide, okay? So that is static friction coefficient, not force. It's the coefficient that's given, not the force. And now the question is, how far from the center of the record can the coin be placed without having it slip off? So in that video, you saw a coin start slipping up once the speed goes higher than a certain value. And it also depends on how far it is from the center. That video does not demonstrate that. If you ever been to merry-go-round, it's a lot easier to stand near the center, okay? If you are, center of that disc of the merry-go-round. So if you are standing right at the center, no matter how fast it goes, does not matter. You can stand just fine. But if you are standing there and there is no rail to hold on to, then once it goes faster and faster, what happens? It becomes difficult. So you start slipping off, just like a coin in that case, okay? And you are less stable than the coin, so several other things can happen. But the idea is same, okay? So now, friction coefficient means, let's say we can write friction force from the friction coefficient. So the information about force is there. And this is speed, force, speed. And it says how far from the center. So that would be a radius, okay? Radius and speed, that gives us acceleration. So we need to keep that in mind in, circular motion. Radius and speed gives you acceleration. or radius is related to acceleration. Speed is related to acceleration in circular motion. So now we have information about force and acceleration. So that means it tells us we should be using dynamics or laws of motion, not the kinematics. Okay. So that's why, so that's how we know, we can tell, okay, I need to use Newton's laws of motion or dynamics to solve this problem. So when we decide, okay, I need to use Newton's laws, so that means I need to write net force. So that means I need to draw a free body diagram. So what forces are acting on a coin that is sitting on there? We said there was a friction force acting, and it is static friction force. What other forces are acting on this coin when it is sitting on a horizontal table? Can you draw a free body diagram of that? Right? So only new thing is this static friction force. Other things we've been using, since it is sitting on some sort of surface, they're going to be normal, right? Another one going to be weight or force of gravity. Okay. So let's not just call gravity. Rather, we need to be specific. Either it's going to be acceleration due to gravity, that means it is G, or force of gravity, which is mg. Okay. So there is that difference. So gravity is bit blanket statement. Now we know better. So that's how we need to speak, write, and talk. Okay. Okay. So that's why you see that. And I'm using this as a horizontal, as a x-axis here, y-axis. Or we can say, okay, that is the radial one because this is moving in part of circle. Okay. So we are looking for radius, and it is inside the acceleration equation. That is, AR is, so in this case, it's given in terms of angular speed. So I'm writing that instead, b squared over r. So I'm going to write that, okay? So that's there. So that means we are looking for acceleration, okay? Radial acceleration. So radial acceleration is acting in that direction. So that tells us we need to write equation in that direction. So we need to use equation in radial direction. So that means sum of forces along the radial direction is equal to mass times acceleration in radial direction. So that's the formula. So how many forces are there in radial direction in our free body diagram? Can you see that? How many forces are there? 1, 2, 3. Can you type that? Along the radial direction. This is radial direction. So you are just looking at free body diagram and counting the number of forces. And I don't see response. I don't know why it's so difficult. It says radial direction. What is radial direction? Same as x. Okay. So there is only one force acting in that direction. The N and mg, they are acting in vertical direction here, not in radial direction. Okay. So that's that. So that means I can write sum of force as just one force, okay? Oh, by the way, which direction should you choose? Positive. Here I'm choosing towards the center because acceleration, radial acceleration always points towards the center. I like to choose that as a positive. See, although it's kind of pointing left, and in other situation, maybe we may have chosen right as a positive and left as a negative. Here I am choosing this the way I have drawn, left as a positive. Why? Because AR points towards the center. Okay. So while you solving radial or circular motion problem, you want to choose one axis in the radial direction and choose positive towards the center of the circular path. That way the acceleration always remains positive. And in this case, even force is positive. Okay. And in this case, it says slip off, right? It's slip off means it's like it just starts to move. So maybe it is the Fs max, not just Fs. Okay. Sometimes I may just write Fs even for the maximum value. But here, let's be more specific. And then mass and acceleration is positive by our choice. Okay. And this is R omega squared. Okay. So we need to solve for R. And this one over here, see the friction coefficient is given, friction force is not given. So we need to write this as coefficient times normal force. Remember, this is the definition of static friction force. So I'm using that. So it's in equation sheet, but you should keep that in your vocabulary as well. So that's the left-hand side, and right-hand side is just mr omega squared. Oh, there is n. Now, how much is n? Do we know n? Normal force. Do we know normal force in this case? How do we find that? Ooh, how do we do that? So whenever I need force, I look at free body diagram. And in this case, normal force is in vertical direction. So that means I need to look at the free body diagram in vertical direction. And there are two forces acting in that direction. So N is balancing the mg. So if I were to use sum of forces along the y direction 0, see the point is not accelerating up, right? So that means it's going to be, let's say, if we choose up as a positive, positive N minus mg is 0 means N is mg. So we can use that here instead of N, mg. Oh, mass is also not given. How do I solve this problem? The thing is, see, the beauty, the mass cancels. In many cases in physics, mass may cancel. So sometimes I receive emails saying, in that problem, looks like I need mass, but mass is not given. How am I supposed to solve that problem? Okay, sometimes I get that kind of email. So what happens is, if mass is not given and if you need mass, just write M for mass, keep doing things, and most likely it's going to cancel at some step if you do it correctly. Okay, so mass here cancels. So now I can solve this one for R, means mu s times g over omega squared. Okay, still need omega with correct unit. See, omega is there, but the unit is not there, okay? So this is revolution per minute. So omega is 33.3 revolution over minute. Per minute means that, right? So let me clean this thing up a little bit here. So we want this in terms of radian per second. Okay, so we have to convert minute into seconds, which we all easily know how to do it. How about revolution to the radian? So one revolution is how many radians? One revolution is 360 degree. We know that. One complete revolution means 360 degree. And 360 degree is how many radians? It is 2 pi radians. So we can use that. So for the revolution, what I'm going to do is, okay, there is revolution per minute. So let me copy that. And then I want to get rid of revolution. So one revolution, and I want radian means 2 pi radian. So I'm converting and getting rid of that revolution by this factor. And minute, you know, 1 minute has 60 seconds. So the minute cancels, this revolution cancels. Now you are left with radian over second. And that's what we are looking for in terms of unit. All you need to do is just multiply those numbers. For the pi, you can use 3.14. Okay. I think I have done all these things here. And turns out it is 3.5 radian per second. Okay. And once you plug that into this R equation we have with this omega, then what do you get? You get 0.08 in meters. So how do you want to look at this equation? Something was moving in horizontal circle sitting on some sort of surface, right? So person is standing on merry-go-round, coin on rotating platform, some sort of rotating platform, okay? Person is standing on some sort of rotating platform. All situation you can use same idea, same method, okay? So now let's go to the rotor ride here. So in this video, and I heard there is like a rotor ride even somewhere in near the downtown Denver. I haven't been there, but it is a big cylinder and there is this floor and you stand there. Once the cylinder starts spinning, after certain speed, the floor starts dropping, but the portion does not drop. Oh, it looks like gravity is gone. Okay, portion is floating, so gravity is gone. So what does that mean? How do we analyze that kind of problem? So think about, okay, so weight is still there. Gravity is not gone anywhere. So mg is still there. So if portion is not coming down, so right now portion is not coming down because mg is down and normal force from the floor is there. But if floor is gone, normal force is gone. So what balances the weight so that the portion is in place without falling with the floor? Keep that question in mind. So what force keeps portion in place, okay? Or keeps portion from falling down, okay? And then what is the direction of normal force in this case, okay? When portion is spinning on that cylinder. So I'll show you the video.
Abby, don't move your arms, Justin.
That spring, that's yes, you are flying.
It's okay. That's what's supposed to happen.
So I don't know if you are able to hear this, but the kid was saying, I'm flying, right? And you can see, indeed, seems like it's flying, okay, when it's rotating. Floor is down here, person's feet are there, so nothing is supporting in that direction here. So when the person is something like this, what are the forces acting? Or even better, which free body diagram best describes this when this person is, let's say, stuck there, just like we saw here at the end of video. It was on this side, but here it is on this side. Assume this person is right here in this corner there, okay? Oh, oops. There are colors, but no A, B, C, D. Okay, I'll let you pull, and you have, let's say, a minute. Okay, so forces are not labeled. Which one you think are the forces that's acting on this person? So before you draw a force or think about a force, also think, is it contact or long range force? If it is contact, where is it coming from? Okay. Oh, forgot to warn. 30 more seconds. 5 more seconds. 5, 4, 3, 2, 1, and it stops. Okay, let's see what we got here. We have more B than anything else, but A, D, and E are competing. Okay. So B, let's say B. So let me ask you a question. So that force is pushing the person towards the wall of this ride, right? So that's how it is drawn, right? So what force is there? Is that tension force? Probably not. It is not because no string attached, right? What force is this or this or this? What forces are those? Where is it coming from? Do you know the source? Long range force, this is gravity that can act without touching and vertically down, makes sense. How about that force on the backside? Okay. Okay, contact friction. Okay. So contact friction. So which way the friction should be acting here? Which way person is trying to slide here? Right? Whenever we need to, whenever we draw the direction of friction, we know it's opposite to the motion or the direction up, direction opposite to the motion or the direction at which, opposite to which is trying to move. So in this case, is kid, so if we say this is friction force, so that means is kid trying to go to the, center of the circle somehow? This kid is stuck on the wall there. Think about your wall, and you are stuck on the wall, like, oh, side of this chair or wall is standing there. So now force of gravity is pulling you down. So that means you are trying to slide down. So that means friction must be acting up. Looks like there is friction, yes, but that is not friction. So this is friction. This is weight. What is this? Is someone pushing this kid to the wall? Is some sort of push force, applied force there? No, there is no such force. So that's why this is incorrect, this is incorrect, this is incorrect. But this kid is, here stuck on the wall. So that means there is this normal force. And remember, since this kid is moving in circle, there must be a force towards the center of the circle, at least one force. There must be net force towards the center of the force circle. Okay, so what that force possibly? It is normal force. So this one is missing that friction force, so that's why it is not correct. So now what are these? So this is normal, this is static friction force, and this is weight. Okay, mg. So A is the correct free body diagram for this. So yes, it is very difficult. Okay. So that's why I emphasize so much about contact force and where it comes from. So before you draw a force, make sure to confirm the source of that force, where it's coming from, okay? That way chance of being wrong is less. And there is a problem directly related to this one here. So since we ran out of time, we will be doing this problem in another class, okay? So in the midterm, there are going to be materials from up to this slide, okay? There are going to be materials from up to this slide for the midterm. Okay, folks? So if you have quick questions, stick around, or else I'll see you next class.